Welcome back to this science quest. You've reached the third level of Energize. Let's review our key point. These are the things that are most important as we discuss our quest. Energy exists all around us in many forms. Energy can never be created or destroyed. It is transferred from form to form and can move from one object to another. Heat energy moves from one object to another through conduction, convection, or radiation. Electrical energy is constantly moving. An electric current flows through parallel and series circuits quickly and invisibly from one place to another using conductors and insulators to produce electricity. Level 3 of Energize is on magnetism. During this level, you will learn how magnets are designed, observe how they work in the real world, and discover the relationship between magnetism and electricity, which we discussed last level. Let's first begin by talking about Mission 1's objective. Mission 1 is on magnets, so our mission objective is to describe how humans observe magnets in the world. That means if we see a magnet, how do we expect it to act? How do we expect it to behave? So as we're going through here, be thinking about how do we expect a magnet to behave as we observe it in the real world. Our challenge questions is first, what is a magnet, and how does it behave? And our second challenge question is, how is a compass like a magnet? Let's first talk about magnets and magnetic fields. Magnetism and electricity are very similar. In fact, they behave in very similar ways. The definition of a magnet is anything that attracts other things made of iron, steel, and some other metals. Here that tree map shows the three main types of magnets. There's a disc magnet, a horseshoe magnet, and a bar magnet. Of course, you might see the magnets on a refrigerator. They might not look like this, but these are the three main types of magnets that scientists use and experiment with. Each magnet has an invisible field around it that goes out in all directions. That field attracts metals that are nearby. If it comes in contact with a metal that's within that field, it will be attracted to it. And we'll talk exactly about what that means to be attracted to something here. Next slide. The shape of that magnetic field depends on the shape of the magnet itself. So a disc magnet is going to have a magnetic field probably in the shape of a circle. A horseshoe magnet might have its magnetic field come out from each side of the horseshoe. And a bar magnet is going to have its magnetic field kind of look in a semicircle around each side of the magnet itself. The magnetic field is strongest at the magnet's poles. What are magnetic poles? All magnets have two poles, what scientists call a north-seeking pole and a south-seeking pole. Opposite poles have opposite charges. Think back to our level on electricity. What things in electricity have opposite charges? Protons and electrons. Protons have positive charges, electrons have negative charges, and they are attracted to each other. Same thing with magnets. A north-seeking pole is attracted to a south-seeking pole. Unlike charges attract each other, while like charges repel or push away from each other. The picture shows the South Pole being attracted or pushed towards the North Pole. The bottom picture shows South Pole. If they're next to each other, they're going to try to move away from each other. Same thing with the North Pole. If they're right next to each other, they're going to try to pull away from each other. They are repelled by each other. And this is important. You might not have known this, that even if you break one magnet in half and to create two new magnets, the two new magnets will, in a sense, inherit a North Pole and a South Pole. That North Pole and South Pole will still be there. In other words, they cannot exist without the other. A magnet cannot exist without a North Pole and a South Pole. Very important parts of a magnet. How is a compass like a magnet? Well, you might remember from Amazing Earth that Earth also has a magnetic field because Earth's liquid iron core. There are three or four, depending on how you look at it, 3 or 4 different parts, 3 or 4 different layers inside of the Earth. In the very middle is a liquid iron core. That iron core is constantly spinning, and it helps create this magnetic field that is invisible around the Earth. As the Earth rotates, as I said, that liquid produces an electric current, which creates a magnetic field. The Earth's North Pole and Earth's South Pole are where the pull from that magnetic field is the strongest. And a compass points north because the needle is magnetic and it is attracted to the Earth's North Pole. So what type of magnet do you think that is that points north? If it's attracted to it, is it going to be a north-seeking pole or is it going to be a south-seeking pole? It's going to be a south-seeking pole because it is attracted to the North Pole. Remember, opposites attract. Once you know which direction is north, you can easily then determine south, east, and west, as long as you know your cardinal directions. In this lesson, we learned about how magnets work, what a magnet is, what they are attracted to, what they are repelled from. And we also learned how Earth has its own magnetic field, and that's how a compass is able to be used, because a compass is designed to be attracted to that North Pole. If you are ready, if you've answered the questions after going through the rest of the videos in this mission, you will then be ready to take the checkpoint. If you have any questions, please let me know. Remember to take good notes, to use good test-taking skills and strategies as you are conducting your checkpoint.